start this recording. Oh, I guess I should share my screen too. That could help. Otherwise, it's just a black screen with my voice for an hour and 20 minutes. That would be really boring. More boring than this. All right. So, before I pick up where we left off last day, let's see here. Is there anything I wanted to say? Oh yeah, the lab tomorrow. I'll make it so that you can just do it on your own time. I'll be in the room next door if you have any questions or if you want to just use that time to work on it, but it's completely optional. And so I'll just set it up so that you could just do it whenever. You don't have to come to the lab time. And since I'm here this weekend anyways, I may as well come to lab. Sometimes I'll be like, just work on it on your own. Don't want to be here. Okay, but tomorrow I'll be there if you have questions or if you just want to use that time to work on the lab. That's good. Okay, picking up where we left off, and maybe I should make a note of that first. Seems unfair. Lab number 2, it gets weird because then next Friday there are no classes, right? September 30th. So then we miss a lab day. That's okay, we'll survive. But it kind of gets us behind, but that's okay. So lab number 2, I will set it up so you can do it on your own time. I will be in the lab room during our lab in case you have any questions.
It's already open, right? Or no?
Lab 2?
Yeah.
No, because I haven't made it. Yeah, I know. I have a lab 2, but I don't like it. So I'm gonna have to fix it. Just lab 1. So I'll be in the lab room during our lab time in case you have any questions or obviously just want to come and work on the lab. Do you guys have like stuff going on? My attendance in my last class was like terrible. Now there's a couple of people missing in this one too. Do you guys have a lot going on this week? Oh, not really. So people are taking the opportunity. It's like, it's not very busy. Hit the beach.
I'm still going to the library till like 9 o'clock. Thanks so much for joining online.
Oh yeah, I did see Darmpreet on there. Nice. So that counts. That counts. And there's not that many of us in this class. But I was just thinking, yeah, my other class, I kept waiting for them to show up. No one showed up. It's just like a little group. Okay, so that's what we'll do for the lab tomorrow. Just kind of can work on it anytime. Doesn't have to be during the lab. All right, and you'll have a week to do it. I'll make it due, I guess, Friday the 30th, or I could do the end of the weekend. Sometimes I like to do it the 29th so that you don't have it hanging over your head over the long weekend. But maybe that's not nice. All right. So when we're talking about, so to pick up where we left off, let's do a little review. And maybe my review will be just grabbing this so we can just talk about it because it's in your notes. So from last day. Just to kind of reiterate. So we were talking about two categorical variables. We also noticed that the textbook doesn't talk about how to visualize, even though before it was clearly talking us through, okay, first, how do we summarize it? Then how do we visualize it, or vice versa, right? How do we visualize it and summarize it? And for some reason, they skipped the bar charts, maybe because they're obvious, and I don't know, but I just wanted you to have everything. Okay. And so to visualize the relationship between two categorical variables, we can use either a stacked bar chart, which within the categories of variable one, we can stack the counts of variable two, right? Or I prefer the side-by-side bar chart because it's a little bit cleaner to look at, right? And I just find that it's easier to compare counts or proportions, right? We can use proportions as well, and often we should, but sometimes we don't. It just makes it easier to compare the different groups, right, among the two variables. Yeah. So to summarize the relationship between two categorical variables, we use what we call a contingency table, which we've seen in the past, but I just want to remind you. So, I guess I'll show that this is the end of stuff from last day. To summarize, the relationship between two categorical variables, we use a contingency table. Oops, I should say table. Okay. Contingency tables can be either of the raw counts, or usually we prefer the percentages or proportions rather. Okay, so it can be raw counts or proportions / percentages. Usually if we're talking to a client, we don't say 0.34, we would say 34%, right? Because that's just how we talk. But in terms of math, we always use proportions, right? So it depends on what you need to do with these proportions. But in terms of reporting, you're going to report percentages. Okay. A contingency table is essentially a pivot table if you're using Excel, right? And so a contingency table do they make you use Excel at all in this program? I know Bevan's a huge Excel fan. I'm not. But I know I think it just depends on what you're used to. But I'm not a huge fan of Excel. I think it's really annoying, really slow. But a contingency table is a pivot table in Excel, right? Looks something like like this, if we're going back to variable 1 is A and B, whatever generic groups A and B are, and variable 2 is either pink, orange, or green, then we could set up a table, and I'll put it on the fresh page here, but it would look something like group A or B, and that's variable number 1. And this is where I did, can you imagine if I used orange for the pinks and green for the orange? And orange for the green? That would be so crazy. And so confusing. Yeah. But what did I have? I'll stick with what they are. Pink, orange, and green. Right, and that's variable number 2. It doesn't matter which one is which, right? You can interchange them. It would just make a 3x2 table instead of a 2x3 table. But in terms of information, it doesn't change anything, right? So that's fine. And then usually we add on the totals. I'll make it like a ghost here in gray. Total. And then the total. Okay. Those are the marginal totals. Right. We can add the totals in the margins, or add the totals to the margins, let's say. They don't have to be there, but they usually are. And then dark green here. This is the total sample size, which is your N, of course. Okay. I think we did like a lay of the land situation. So we've talked about 1 numerical variable, 1 categorical variable, 2 numerical variables, 2 categorical variables. What if I have 1 numerical and 1 categorical variable, right? Notice that I'm not specifying the response variable, which one is the response variable. And that's because it doesn't really matter that much, as you'll see. Okay. But what if we have one numerical and 1 categorical variable? I suspect I've been highlighting them so you can kind of find them. All right, so now I have 1 numerical variable and 1 categorical variable. One thing that's not very telling is I could make a couple of different histograms or box plots if I wanted to, split up by the categories, right? So you've probably heard of, I think it's facet in ggplot, where it breaks it up, right? And so that's one of the things that you could do. Or I prefer to have side-by-side box plots. As soon as I have 1 numerical variable and 1 categorical variable, then to do comparisons between the groups or the categories, then I like to have side-by-side box plots. Okay, so to visualize, we can make a histogram. Or box plots for each category, right? So make separate histograms and box plots, but that doesn't really tell us much. Okay. So we can make a histogram or box plots for each category. or side-by-side box plots. Oops. This is what I prefer. Why? Because it allows me to draw comparisons on the same scale. Often if we tell R to make a couple of different histograms, it just adjusts the scale. So unless you adjust the scale to be the same, then it's really hard to compare those two distributions. Whereas if I have side-by-side box plots, then they all have to be on the same scale, and then I can compare them. So this is what I prefer because it allows comparisons across the groups. So it allows comparisons across the groups on the same scale. So for example, that would look something like this, where you have your numerical variable. And let's say you have A, B, C, which is your categorical variable. Usually R is smart enough to recognize that if it's clearly a categorical variable, it'll just make side-by-side box plots if you just use the generic plot command, right? If you use a numerical variable on the y-axis and a categorical variable on the x-axis, it'll just create that, which might look something like this. I don't know, just a generic side-by-side box plot. There are a lot of things that you can talk about here, right? If you're talking about, if your response variable is the numerical variable, if that's the one that you're interested in, well, then you're still going to rely on, okay, C overall just has higher outcomes, whatever the numerical variable is, right? The values tend to be higher for group C and lowest for group B, and kind of most stretched out or maybe something like that for group A, right? Most variability in group A, that kind of thing, right? And so whereas if you flip it, right, it doesn't, so this is why I said it doesn't really matter if the categorical variable is the response. So now let's focus on from the categorical responses point of view. Well, then I'm still going to be talking about the same stuff, right? Overall, the outcomes are the highest for group C, right? Lowest for B, most variable in A, that kind of thing. Should have stretched A out more so that it was clearly something like that, but okay. So, and maybe I will. How about that? So for this example, right, we would say something like the outcomes are generally higher. It depends on what the numerical variable is, right? Are generally higher in group C, lowest in B, and most variable in A. Or something like that. There's lots that you can say about side-by-side box plots. Usually you'd want to look at how the minimums and the maximums compare. So notice that there's no overlap between B and C here, for example, right? That would be worth noting, right? The minimums for A and B are relatively similar, that kind of thing, whereas the variability of A is much larger. Lots of things you can talk about. If you were wishing there was a fancier thing than a box plot, there is the violin plot. Because the box plot is hard, right? Because we know that, okay, the distances between each of these components, right, covers 25% of our data as we go along, right? And then it highlights any outliers by the 1.5 IQR rule. Right? Those are all things that we know already. But it's hard to see the distribution of the data within these 25% blocks. So then the violin plot really just kind of shows it by kind of this violin looking thing, shows the density of the data. So we could also use a violin plot, which is a side-by-side box plot, essentially, which is a side-by-side box plot, but instead of just boxes and whiskers, it shows the density of the data as well. It shows the density of the data as well. So I'm gonna have a hard time replicating this graph as a violin plot, but here I go, I'm gonna try. I've got A and I've got B and I've got C, and channel my inner violin drawer. That wasn't very good. It's supposed to be even. A mirror image, like a Christmas tree. It's not very good. Now I'm just making a Christmas tree. Those are terrible. Is there a violin emoji that I could do here? Hey. Oh, it's the font size. It's supposed to look like that, but they don't. That's okay. I think you get the idea, right? So instead of just the boxes, it actually shows that, okay, here's what's going on with this data. And then as it tapers off towards the top and presumably the bottom, right, it'll show that. Okay. 2 numerical variables, 2 categorical variables, 1 categorical and 1 numerical. And what we noticed is it doesn't really matter which one is the response. We would graph them the same way. Okay. In terms of summaries, I guess I didn't have summaries for 1 numerical and 1 categorical. But we could just break up our numerical summaries into by categories. That's usually what we end up doing. So to summarize, often just numerical summaries broken up by the categories. Broken up by the categories. I feel like that's another one that, because I didn't have it in my notes, now the textbook focused on visualizing instead of summarizing. So glad I caught it. Okay. Numerical summaries mean the summary command usually in R, or something a little bit fancier, but in general, just the numerical summaries. All right. What do we do if we have 2 numerical variables and 1 categorical variable? That can happen. Two numerical and 1 categorical variable. Maybe I'll change this. There. Think about what would you do if you had 2 numerical variables and 1 categorical variable, and you had to analyze those things. Well, we know that for 2 numerical variables, I'd make a scatter plot, right? And that can be quite telling. And if I have 1 categorical variable, I could either split it up and have multiple scatter plots, right, by the different groups, or I can put them all in the same plot and just have different colors for the different groups. It depends on if that's easy to read or not. Sometimes it's hard to see. So it kind of depends, but yeah, exactly. And I think, yeah, it definitely does it. So when you facet in ggplot for a scatter plot, I think it just does different colors on the same graph, right? It doesn't break it up. I'm sure you could tell it to break it up into separate graphs, but if you're able to see the dots still with the different colors, that's better, right? Because then for the same reason that I prefer the side-by-side box plot, then you're able to do comparisons by the groups, and you don't have to kind of map back and forth. But to visualize, make a scatter plot with different colors or symbols, depending on which group they're from, right? You should use symbols. If you're printing in black and white, you should use symbols, of course. Otherwise, color is really tough. So make a scatter plot with different colors or symbols to represent the categories. This allows for comparisons across the groups, right, on the same scale and on the same graph. This allows for easy comparisons between the groups. If that's too, I'll say busy, right? If there's too much going on and you actually can't see anything, then you're going to break them up. Okay. So if different colors or symbols make your graph too busy, right? So difficult to read. I'll say that in bracket, difficult to read. Then you should split up your scatter plots and look at individual scatter plots by each category. Then create individual scatter plots for each group. Scatter plots, right? We talked about scatter plots. They're our go-to, but we can also kind of take it one step further. There's hexagonal binning or the contour plot or the heat map, right? Those are just kind of fancier versions of a scatter plot. So when I say scatter plot, you say how high? No. When I say scatter plot, right? That can be replaced with a fancier version, but in general, or hexagonal binning, contour plot, or a heat map, just to name a few. Have you guys watched any talks by Hans Rosling? He's a Swedish guy, he's dead now, but he was an idol of mine for a long time. I wanted to be able to produce reports like he did, or kind of produce material like he did. He was the first one that I saw that had these kind of moving bubbles, and he looked at kind of population changes. And all I wanted to be able to do is make these like growing, moving bubble charts. So bubble charts are another way that you could do it. You could have the size of the bubble be something, right? Mean something. And then he moved them. It was so cool. Maybe I'll find it and I'll post it on our Moodle page, just in case you haven't seen it. All right. Oh, feels like plenty for just kind of a basic toolkit of how do I summarize and how do I visualize all these different combinations. Of course, there are others, right? But just to have a general toolbox is really good. And before we start chapter 2, any questions? When is nap time? I know. You and me both. All right. So where's my page break? I'll start it on a fresh page here. Chapter 2 is called Data and Sampling Distributions. Or I have a note to myself. Is that what it's called? Or is it data distributions and sampling distributions? Ah, those sound the same to me, don't they? Yeah. I don't know why I have a note here. I think it's going to be one of those things that I realize halfway through. Oh, that's why I had that note here. But for now, we'll ignore it. Data and sampling distributions. Let's remind ourselves the differences between data distributions and sampling distributions. So data distributions of the data. Okay. So the data distribution is well, I'm trying not to use the word distribution. It's the distribution of the data. That's not very helpful, right? And so maybe I'll explain how we get it. So when we have raw data, so just a plain old variable, when we have raw data and we make a histogram of it and look at the shape and the center and the spread, the shape is the distribution of the data. And when we have raw data and we make a histogram of it, that means it has to be numerical. I think we're kind of past that. Okay. So, and we look at oops. The shape, center, and spread. The shape is the distribution of the data. Distribution of the data. Okay. Sampling distributions. We only saw one explicitly, but sampling distributions have to do with the distribution of the sample statistic, right? Or a statistic is the sample, right? And so now we're talking about the distribution of X bar, for example. How do I expect a collection of means, even though I've only collected one sample, knowing how means behave in general is going to be useful, right? We use that to do hypothesis testing. We use it to build confidence intervals, right? And so we use the sampling distribution at kind of the core of statistics. What we're going to find is that that's kind of the old school statistics, right? When we didn't have computers. So today I want to show you what we do kind of more now is move away from these sampling distributions, although we don't move away from them, we still use them, but we generate them ourselves. Okay, so let's just talk about sampling distributions. So the sampling distribution is often a theoretical distribution of a statistic, right? And so the distribution of a, I'm going to say sample statistic, even though that's redundant, right? Because a statistic is from the sample, but just to emphasize that, the distribution of a sample statistic like X bar, right? That's a sample statistics. It's a measurement from the sample. So that makes it a statistic. Yeah. And in the past, right, we've established by the central limit theorem, oh boy, that sounds important. It is, well, not so much anymore because we have computers, but of course it's kind of what built statistics is. So the distribution of a sample statistic like X bar and from the central limit theorem, we know that X bar follows a normal distribution centered on the mean, the population mean, with a standard deviation of sigma over root n. Or usually we convert these and we convert them to X bar and S because we don't have mu and sigma. I'm skipping ahead in my notes here, so it could get confusing. That's okay. So here, the central limit theorem, this was a long time ago, but knowing that the X bars are going to be distributed following a normal distribution, that's what lets us use t-scores, for example, or z's for proportions. So remember, we calculated test statistics, and it's because we assume that we know the sampling distribution. In this course, we're gonna build on that. We're gonna move away from it a little bit and say, okay, well, what if I didn't have to assume that it followed a normal distribution, for example, right? What if I just created my own distribution? I just looked at it and I made calculations off of this distribution that I made, right? Using my own data. So that's where bootstrapping comes in. But let's just rein it in a little bit. Right. Yeah. So it's pretty interesting. This problem of having too much data. Statistics as a field, they were never used to having that problem. That was never a problem. It was always get more data, get more data. But what we find is that when you have too much data, and there's a really interesting example in the textbook where I think it was it the Literary Digest or something? They mispredicted a presidential win because they had too much data. And so it wasn't giving them enough, or it was kind of diluting the information. Whereas Gallup polls are still a thing. It's a huge firm that does surveys, usually in the States, but so Gallup polls are a thing still, because he correctly predicted who would win this presidential election with a much smaller sample, but it was kind of a more thoughtful sample. Okay, so now we're kind of in limbo. We have all this data, but we don't want to have too much, and it gets messy. So let's take it back here. To collect data, of course, we rely on sampling, right? Or some sort of data collection technique. And our sample, we know our sample has to be representative of the population, otherwise it doesn't tell us anything, right? And so in order to achieve that, we have to have a random sample. Just at its core, our sample has to be random. So to collect data, we rely on sampling. And maybe I'll say from a population. from a population, of course. And before I get too far here, I'm just going to draw a line here because I'm starting a fresh idea. I just wanted to talk about the title of the chapter because that's where we're going. Now let's take it back. Because before I can have any mean or even a collection of means, I have to collect a sample, find the mean, and then collect another sample, find the mean, right? So that's where we have to start, right? So to collect data, we rely on sampling. And in order for a sample to be representative of the population, we have to use random sampling. And in order for our sample to be representative of the population, we need to use random sampling. Oops. I think in that presidential election that they mispredicted so badly, I can't remember exactly the story, but I guess they had all these people that they could survey. And so they thought, okay, well, I've surveyed, 10,000 people once a month. That's a lot of people, right? So how can that be bad, right? Surely I'm capturing the general population here. Whereas Gallup, I think, only surveyed 2,000 people every month, but he was able to get more reliable results because he was randomly sampling those 2,000, as opposed to, I think it's the Digest, who just had a list of people that they would contact and just kind of ask them. Random sampling. What does it mean? So by definition, random sampling is when every individual in the population has the same probability of being selected into the sample, right? That's a really important idea. It means that everyone has the same opportunity, I guess. Random sampling. Each individual in the population has the same probability of being selected into the sample. The opposite of that is, of course, biased sampling, right? Where we would be systematically favoring a group or a group of individuals. So here versus biased sampling. Which is systematically favoring certain individuals. Systematically favoring, oh man, certain individuals. Kind of the opposite of random sampling, right? Each individual does not have the same probability of being selected into the sample, right? Each individual does not or I guess individual in the population, I should say. In the population does not have the same probability of being selected into the sample. Not have the same probability of being selected into the sample. Highlight that. Basically the opposite of random sampling. Bias is unavoidable often. So we have to be able to deal with that. And so sometimes we just need to recognize kind of the restrictions that bias puts on our interpretation of the data. So if we think about restaurant reviews, right, then we know I want to be a person who leaves reviews, and I'm not. I don't write reviews, even if, something amazing happened or something terrible happened. I don't write reviews. So I'm just not a review writing person, right? And so all of us who are not review writing people are not accounted for in the sample, right? So now all of a sudden we don't have the same probability of being included in this information that's being presented in terms of restaurant ratings or whatever, right? And so, well, what can we do with that, right? We still have restaurant ratings and people talk about their restaurant rating. Oh, we're 4.9 something. That's amazing. And I use ratings. Why? I can use ratings to compare restaurants still, right? Because people who are leaving reviews, they're all going to be the same. It doesn't matter, right? So I can use it to talk about, okay, how this restaurant compares to this restaurant and how this one compares to this one. But I can't use it to say, oh, this is how everyone feels about this restaurant. That's not necessarily the case, right? So as long as we recognize the limitations that we have with biased sampling, that's okay. So bias is often unavoidable. Oops. Which means that we'll need to just be able to recognize the limitations. Which means we must be able to recognize its limitations. Right. So for example, restaurant reviews, right? Restaurant reviews are biased, right? Because some people don't leave reviews, right? Oops. Some people don't leave reviews. Some people only leave reviews if they had extreme experiences, good or bad. And then the list goes on. But just for example, we'll do etc. Not very fair, right? But I think we can all kind of think of some reasons why restaurant reviews would be biased, right? But we can still use restaurant reviews. We can still use restaurant reviews. Oops. To compare restaurants. But we can't talk about how the general population feels about each individual restaurant. I'll start a sentence with but, even though you're not supposed to. However, there, that's allowed. However, we can't use those ratings to talk about the general population. We can't use the ratings to talk about the general population. So what they were finding kind of as the shift of, okay, once we have all this data, we got all giddy and excited. This is what we've been waiting for, all this data, what are we supposed to do? But what we're gonna need to focus on is that data quality is a lot more important than data quantity. Okay. And so I'll say, even / especially, I'll say. Even with big data, or especially with big data, which is just kind of a loose term that we use once we hit kind of 2 million data points, that kind of thing. It can be smaller or bigger, I don't know. Generic term, too much to handle, right? In my mind, big data is any data set where you would not want to go through and read all the comments reasonably, right? If you're letting people leave comments, then it's probably a small data set, because otherwise you'd be completely overwhelmed. Someone would have to code those. So in my mind, big data is just kind of a little bit out of reach. Don't want to be looking at all of it. So even with big data, data quality is often more important than quantity. Okay. So random sampling, right, can reduce bias, not necessarily eliminate it, but helps reduce it and improve the quality of the data. So random sampling can reduce bias and improve quality. And quality, of course, is how representative this sample is of the population. Right, so by quality, I mean how representative it is of the population. Remember, that's our goal. There's lots of random sampling techniques besides simple random sampling, but usually the one that we go for is just simple random sampling. We attach a set of random numbers to our data set, and then I can sort those, pull the top 50 or whatever. There's obviously packages and stuff in R that do it for us, so you don't have to worry about it. But random sampling is the way to go. So just so we have a little reminder here, some random sampling methods include simple random sampling, which is SRS. In Stat 230, we talk about stratified random sampling or even multi-stage sampling, right? Those are more advanced, but our go-to is going to be simple random sampling, of course. But we've talked about in the past stratified random sampling, multi-stage sampling, etc. I'll say, see the further reading. They've got all this further reading suggestions. Now I'm not asking you to do any of that further reading, right? But sometimes it's interesting, right? If you want to learn more, here are some good resources for that. So I think that might be useful just from the textbook. See further reading if interested, but I'm not interested. Okay. Okay. Running out of time, aren't I? Oh, bummer. I know that's what you're thinking. Oh, bummer. There's this fun little blip about regression to the mean, which sounds like regression. We know what regression is, right? Linear regression. We kind of touched on that, and we'll do a lot more, right? But it's a little bit different, although they're connected, of course. But regression to the mean is this really interesting phenomenon, I guess, where extreme things tend to become closer to the average kind of as things progress. So one kind of famous example is two parents who are extremely tall, for example. They tend to have tall children, but not as tall as themselves, right? So they kind of regress towards the average. Same thing with two very short parents. They're going to have short kids, but not as short as themselves. So everything just kind of tends towards, especially in biology, tends towards the mean, which is this kind of interesting thing that happens. Okay, so I do want to just introduce it here, and it's in the textbook, but it has nothing to do with sampling. Just kind of a fun thing to talk about. So regression to the mean. And just as the heads up, this is different from linear regression. Although you can imagine, right, if you're on a line, right, you move towards the center. This is different from linear regression. I think there was, I think the example in the textbook is the hockey players. So someone who was rookie of the year, and then the next year they're just not as good, Right? Everyone just kind of goes towards the middle. It's this phenomenon. Extreme observations tend to be followed by more central ones. Tend to be followed by more central ones. So an example, right? Parents that are extremely tall, tend to have children that are tall, but not as tall as themselves. Tend to have children that are tall, but not as tall as themselves. Of course, there's rare instances, right? But in general, that's what happens. Okay. What can I jump into with only 9 minutes left? Not this. Come on, Emily, let us go. All right. We'll save the bootstrap for next week, right? But I do want to talk about the bootstrap. I think this is a good place to stop. If you have any questions, let me know. Otherwise, I may or may not see you tomorrow for the lab. And that's okay. If I don't see you, have a good weekend.